So we can continue the discussion on electrostatics in matter. So today will be the fifth lecture, and it is on the polarization and bound charges. Okay, so we know that in case of insulator or dielectric, there is no free charges. So if you apply the electric field, what would happen is the atoms or molecules inside this insulator will respond to it. And how the atoms are responding to the electric field? If you have a neutral atom, then on applying the external electric field, a dipole moment would be induced. Okay, so dipole moment will be induced in case of neutral atom. And what about molecule? So in case of a molecule, if there is no inbuilt dipole moment, again there can be production of induced dipole moment. Or sometimes what happens is the molecule may have an inbuilt dipole moment. So then on the application of external electric field, the inbuilt dipole moment will try to align in the direction of electric field. So these were the effects of the external electric field on atom and as well as molecule. Now, if you consider insulator, this insulator will contain very large number of either neutral atoms or molecules. So once we apply the external electric field, what would happen is either the dipole moment would be induced or the inbuilt dipole moment will try to align in the direction of electric field. So what would happen is finally we'll get a very large number of tiny dipoles inside the insulator, and it need not be exactly parallel to the electric field always. So some of the dipole moment will be exactly parallel, some would be just have some inclination, some making some angle theta with the applied electric field and so on. Okay, it need not be exactly parallel. Okay, so that would depending upon the type of the molecule and so on. Okay, so this would be the total effect. The pictorially or graphically, you can see that if you apply the external electric field, so there will be alignment of the physical electric dipole moments in along the direction of almost along the direction of electric field. Okay, so and some dipole moments are induced here. So these dipole moments are producing some charge separation. Okay, now how will you characterize this charge separation? So due to this dipole moment, so there will be some charge separation here. Now we have to quantify the effect of electric field on the insulator or dielectric. So we can quantify the effect of electric field within an insulator by introducing a new quantity called polarization. So what is polarization? So polarization is defined as the dipole moment per unit volume. Okay, so dipole moment per unit volume can be taken as measure of effect of electric field inside dielectrics, or it's also called insulator. Okay, so this measure is known as polarization and denoted by symbol capital vector P. Okay, so remember we'll denote small p for a dipole moment and capital P for polarization. Okay, so polarization is a measure of the effect of electric field inside the dielectric. Okay, so how much is the polarization? Then so more is the polarization, then what means the more is the effect. If less amount is a polarization induced, then the effect is lesser. So we can characterize the response of a material, response of insulator material on the external electric field by a simple definition called the polarization. So next we will discuss what is the potential produced by a polarized insulator. So why we are interested in potential? Because potential is a scalar quantity and it is easy to calculate. And once you find the expression for potential, we can calculate the electric field also. So the potential of a polarized insulator or dielectric. Okay, so we'll use, sometimes the people will ask about dielectrics. So remember they are same. Okay, so the situation is like this. Suppose you have an insulator which is polarized. So since it is polarized, it will be having a very large number of tiny dipoles. I just want to know what is the expression for potential at some point A, which is outside the insulator. Okay, now how to find it? So in order to find that, first we should have some coordinate system. So choose some coordinate system. This is origin. So the vector connecting the origin to the field point, we can denote by symbol vector R. So this notation, the unprimed symbol will give for the field point. So here point A is a field point. Okay. Now how to find the potential at this point? Okay, we don't have a general expression right now, but recall we have already calculated the expression for potential produced by a physical dipole. Okay, so if you have a physical dipole, if you have a physical dipole P, then the potential produced by that physical dipole at point A, which is at a distance r from it, is given by the potential is equal to 1 by 4 pi epsilon 0 p dot rk by r square. Here r is a vector connecting the center of the dipole to the field point. Okay, so we can use this expression in order to calculate the total potential produced by the dielectric. So for that, what I have to do is I have to divide this entire dielectric into small pieces. So consider an infinitesimal volume here. So consider infinitesimal volume d tau prime. So this d tau prime will contain a very small amount of dipole moment dp prime. Okay, so first we will calculate what is the potential produced by this infinitesimal dipole moment at point A. So once you know that expression, then by just integrating that expression, we'll get the total potential point A. So that is the idea. So consider an infinitesimal dipole moment dp prime. So I have to give a vector connecting the origin to the field point, sorry, source point. So this vector is a source. So source would be represented by primed variable r prime. Okay, so I have put prime always here. So r prime. So and then the vector connecting the dipole to the field point, I will denote it by the symbol script r. So our script r is vector r minus vector r prime. Okay. So the what is the infinitesimal potential at point A due to this infinitesimal volume of dipole moment? So that will be equal to 1 by 4 pi epsilon 0 dp, which is the amount of dipole moment dot the vector connecting unit vector connecting the dipole moment to the field point. So now the vector connecting the dipole moment to the field point is script vector r. So corresponding unit vector I can denote as script r cap divided by the script r square. Okay, so dp is the dipole moment by dτ volume. So we know that the polarization is a dipole moment per unit volume. So therefore dp prime, the infinitesimal dipole moment, I can write the polarization times the volume dτ prime, because the polarization is a dipole moment per unit volume. So dipole moment is a polarization times the volume. So therefore this can be written as 1 by 4 pi epsilon 0 p. Obviously that would be a function of r prime dot r cap divided by r square times dτ prime. Okay, now we can have a very large number of such tiny dipole moments. Okay, so if you look at the insulator, it will contain very large number of such tiny dipole moments, and we have to add the potential produced by each such tiny dipole moments to find the total potential at point A. So the total potential point A is simply sum of the potential produced by all infinitesimal dipole moments. So that such kind of summation is nothing but the integration. So I can find the total potential by just integrating the above expression, but the integration is over the source region, not on the field region. So integration over the source region. So the total potential I can write is the integral over the source region, the infinitesimal potential A. So therefore here I can write this equal to 1 by 4 pi epsilon 0 integral over the source region, the polarization is a function of the source point dot r cap divided by r square dτ prime. Okay, so this is the expression. Okay, now we have to modify this expression slightly, so that we'll see in the next page. Okay, so in order to modify this expression, first we look at what is del of r cap, sorry, the del of 1 by r. If you do it very carefully, this del of 1 by r is simply minus r cap by r square. So here del is a gradient with respect to unprimed variable. Okay, so del is a gradient and here we choose the unprimed variable for the field region and primed variable for the source region. Now what would be the del of 1 by script r? If you do it, we'll get the result. It is equal to minus r k by r square. So remember this script r, or the magnitude of script r, is modulus of magnitude of r minus r prime. So actually this r, the script r, contains both the source point r prime, the source vector r prime, as well as the field vector r, the unprimed and primed. But here the gradient is with respect to the unprimed variable, so that is why we are getting minus rk by r square. So if you perform the same differentiation, the same gradient, but instead of taking uh, the field point region, if you differentiate with respect to the source point, that is del prime. So what would be del prime of 1 by script r? So remember the script r is modulus of r minus r prime. So del prime of 1 by script r, that obviously would give plus r cap script r cap by r square. So this result, I can use it here in order to modify the expression for the potential. Okay, so the expression for the potential, which is at point A. Okay, so better don't put point A, so potential at point R. I can write 1 by 4 pi epsilon 0 integral the polarization is a function of r prime dot del prime 1 by script r deta prime. Okay, so we need further modification. For that, we have to use a result from the vector calculus. So according to vector calculus, suppose if you have the divergence of a product of a vector and a scalar quantity, then this can be written as phi del dot A plus A dot del phi. So hence, what would be del prime dot P by script r? So del prime dot P by script r, I can write 1 by script r, because 1 by script r is the scalar quantity, the scalar function, the scalar field, times del prime dot P plus P dot del prime of 1 by r. So P dot del prime of 1 by r, I can write del prime dot P by r minus del prime dot P by r. So therefore, what would be our expression for potential? So the potential is like this. So here, this term can be rewritten in another way. So the potential at point R equal 1 by 4 pi epsilon 0 integral over the source region del prime dot P by R minus del prime dot P by R into theta prime. So I will divide this into two integration, 1 by 4 pi epsilon 0 integral over source del prime dot P by R theta prime plus 1 by 4 pi epsilon 0, the integral over the source region minus del prime dot P by R theta prime. Okay, so again we are going for a result in from the vector calculus, which is called the Gauss's divergence theorem. Which is if you have the volume integral of a divergence, the del dot A theta, this can be written as A dot N into dA. So this over the surface and this integration over a volume. So this is called the Gauss's divergence theorem. So if you use this Gauss's divergence theorem, then again we can modify our expression. Okay, so I can modify which expression, the first one or second one. Obviously we can modify the first one, because first one is a volume integration of a divergence. So this can be written as 1 by 4 pi epsilon 0. Again, integral over the source region, but instead of integrating over the volume, what I can write is P dot n cap divided by R along area dA prime plus 1 by 4 pi epsilon 0 integral this volume source minus del prime dot P by R data prime. So this is a potential at point R. Okay, so if you look at this expression, what is your inference from it? So if you look at this expression, if you see that there is one surface integration and a volume integration. So the first term look like the potential produced by a surface charge distribution, and second expression look like the potential produced by a volume charge distribution. So if you recall, the potential produced by surface charge distribution sigma. So how will you write? So usually the potential produced by a surface charge distribution will write as 1 by 4 pi epsilon 0 sigma of r prime dA prime by r. Okay, so better I will write script r. And potential by volume charge distribution rho. I can write V of r is equal to 1 by 4 pi epsilon 0 integral rho of r prime data prime by script r. Okay, so we have a similar expression but sum of both. So we have a surface charge distribution plus a volume charge distribution. But if you look at an insulator, there is no free charges. So what is the reason behind such charges are coming? Obviously, these charges are produced due to polarization and they are not free charges. And therefore, this charge distribution produced by the polarization are called bound charges. Okay, so they are called as bound charges. So by due to the polarization, we'll get the bound charge volume density or volume bound charge density rho b, that would be equal to minus del prime dot p, and a surface bound charge density is given by p dot n cap. Okay, so we can just see why such bound charges are coming while you are polarizing or while the polarization of the insulator. So bound charges. So physical interpretation. Okay, so if you look at an insulator, on the application of the external electric field, there will be production of a very large number of tiny dipole moments, and it will be almost aligned in the direction of the electric field. So if you look at this, there will be very large number of tiny dipoles. Some of it may have exactly oriented in the direction of electric field, some of it slightly disoriented. Okay, So anyhow, what would happen is if you look at this, if you polarize it, then there will be some charge separation, some minus charge here, positive charge here, minus here, positive here. So there will be some charge distribution. Okay, so obviously due to this polarization, here comes some bound charge density. So there will be some volume bound charge density rho b, and obviously on this side we'll get some accumulation of negative charge here and some accumulation of positive charge here. Okay, so if the polarization is not uniform, then you will get the bound charge density, which is minus del prime dot p, that would be non-zero, and sigma b, that would be equal to p dot n, that would also be non-zero. So that basically comes through the polarization or due to the orientation of the dipole moment. So we'll get some accumulation of charges within the material and as well as on the surface. Okay, now this is case A. So the case A is non-uniform polarization. Now the case B can be uniform polarization. So if the polarization is constant throughout, that is if the dipole moment per unit volume is constant throughout, then what is the case? So I applied some electric field. So if the polarization is constant, then the inbuilt dipole moment will be almost aligning along the same direction. So okay, there is no variation on the dipole moments. Okay, so it will be like this. It will be exactly oriented parallel. So all the dipole moment will be almost parallel to the electric field, and that will be along the same direction because the dipole moments will not change when you're moving from one point to the other point. Okay, so it should be constant throughout. So the orientation of the dipole would be like this. So if that is the orientation, then what would happen if you look at the minus and plus charges? So what would happen is in the interior, the charges would cancel. So in the interior, there is no net accumulation of charges because the positive charge and negative charge are very close to each other, and there will not be any net charge inside the material. So the volume bound charge density would become zero, but obviously there will be accumulation of charges in the interior. At the exterior, that is on the surface, you will get some charge distribution. So there will be some surface charge density. So here, this a problem is these charges would cancel. Okay, so if P is uniform, so if P is uniform, then rho B, which is negative gradient of polarization, that becomes zero, and sigma B, which is P dot n, it is neither zero, it is always not zero if you have a non-zero polarization, because obviously there will be accumulation because there is no one to cancel on the surface, there is no charges to cancel the charges on the surfaces. So obviously there will be some accumulation of charges, some negative charges on left side and some positive charges on the right side. That would always happen in case of if the material become polarized. But the inside, if the charge present or not, that depending upon the uniformity of polarization. If the polarization is uniform, there is no bound charge. So here the rho b equal to 0 and sigma b is non-zero. Here rho b, both rho b and sigma b are non-zero. So this is the physical interpretation of the bound charges. Okay, so we can summarize what are the things we have discussed today. So our aim is to find the potential produced by a polarization. So first we introduce what is a polarization. It is if you apply any external electric field to an insulator or a dielectric, what happens is some dipole moment will be reoriented, or some dipole moment will be induced within the material, so that there will be some net dipole moment inside it. So the effect of this electric field uh, um, on this insulator, we have to use some variable to it, and that variable is called polarization, and which is called the dipole moment per unit volume. So it is a characteristic of a material. So if you take plastic or rubber, the polarization may differ. Okay, so polarization is a characteristic of the material. So it is basically the response of the material to the applied electric field. Okay, so which is defined as a dipole moment per unit volume. And thereafter we have found the expression for the potential produced by a polarized material. So the potential produced by a polarized material, if you look at carefully, it will have two terms. The one term corresponding to a surface term, a surface charge term. Okay, so the one expression is corresponding to a surface charge density term, and the other expression corresponding to a volume charge density term. And we can identify the volume charge density and surface charge densities, but these charges are not free charges, so we have to differentiate the free charges and the charges produced within the insulator due to the polarization. And we have given a new term for it. They are called the bound charges, and their expressions are given this. Rho b is minus L prime dot P and sigma b is P dot N. Okay, so if that is the case, then we can have the interpretation of bound charges. So the bound charges basically produced to the polarization. So once you apply the external electric field, then the atoms or the molecules within the insulator will respond to it. And due to that response, there will be some accumulation of charges within the material. Okay, and so we'll get some volume charge density inside the material, and at outside, that is on the surface, we'll get some surface charge density. And whereas your the volume charge density would become zero if the polarization is uniform. So if the polarization is uniform, then the net accumulation, there is no net accumulation inside the material. So rho b would become zero, and you will get only sigma b. Okay, so with this, we can stop it here. And in the next class, we'll discuss about the Gauss's law in case of dielectric, and we'll discuss about the linear dielectrics, then the boundary conditions, so on. Okay, so before that, you just go through it and study it well. So we'll see in the next class. Okay, bye.